This section covers the odometer test very briefly and continues to show how odometer test results from a thin laboratory soil specimen can be used to estimate the settlement of a thick soil layer in the field. The sample is taken using the cutting ring and assembled into the apparatus with porous stones top and bottom, and the top cap through which the load is applied. The water level must be topped up periodically to ensure that the sample remains fully saturated throughout testing. The dial gauge mounted on top records settlement. This is the plot of void ratio against vertical effective stress on a log scale mentioned in the previous section. The graph is what might be obtained in an odometer test when a sample is subjected to a number of load increments. The kink in the graph is the pre-consolidation pressure, sigma-Vy, the maximum ever vertical effective stress that the soil has experienced. The loading starts off on the left. At this stage, the soil is over-consolidated, OCR greater than 1. Note that the response is stiff. In other words, there's little change in void ratio for an increase in vertical effective stress. Once the pre-consolidation pressure is exceeded, the response is much softer. This is the normal consolidation line, where OCR equals 1. The void ratio now reduces much more for an increase in vertical effective stress. While we have already passed the pre-consolidation pressure of the soil when it was in the ground, we can create a new one for this particular sample by unloading, as shown. Once we unload, the soil is once again over-consolidated, OCR greater than 1. The more we unload, the more over-consolidated the specimen becomes. In reality, there are an infinite number of what we call unload-reload lines, or URLs, all with the same slope. The slope in this over-consolidated region is called the swelling index and is given the symbol C subscript S. There is only one normal consolidation line, NCL, and its slope is called the compression index and is given the symbol C subscript C. The main goal of this section is to calculate the soil settlement corresponding to a change in vertical effective stress. If we know the layer thickness in the field H0, the increase in vertical effective stress delta sigma-V, it might be from an embankment for example, the pre-consolidation pressure sigma-Vy, the compression index Cc, and the swelling index Cs. How do we calculate the settlement delta H? Our starting point is the equation we looked at earlier, that delta H is equal to delta E over 1 plus E naught times H naught. And that's equal to H naught into delta E over 1 plus W naught times GS, because the soil is saturated. So how do we determine delta E in that equation? There are three cases that we must consider. The first is if the soil is over-consolidated before construction and still over-consolidated after the increase delta sigma-V due to construction. In this case, delta E is calculated based on the slope of the CS line only, using a y is equal to mx type approach. The logs make the expression look more complicated than it really is. Plugging this expression for delta E into that on the previous slide, we get the expression shown for delta H. This allows us to work out the settlement in the field. The second case is when the soil is normally consolidated before construction and obviously still normally consolidated by the end. The formulation is similar to before, except we are now using the Cc slope, which is typically 5 to 10 times higher than CS. The third case leads to the longest expression of the three. It has two parts, as the soil starts over consolidated, but becomes normally consolidated after the load is applied. In other words, the initial and final vertical effective stresses straddle the pre-consolidation pressure. So both the CS and the CC slopes are used. Some general comments about this method. The method is thorough, but CC, CS and sigma-Vy can be difficult to predict reliably from odometer tests. CC and CS are relatively constant and not stress dependent. Use case 2, in other words the case where you start normally consolidated and finish normally consolidated, if at all in doubt about OCR, as this is the most conservative approach of the three. Empirical methods for CC serve as a check on odometer values. An alternative to this method is what's called the MV method. If the vertical effective stress is plotted on a normal scale instead of the log scale we have been using, we get this curve instead of the two straight lines. The equation on the top defines MV, essentially the slope of the curve between stresses sigma-V and sigma-V plus delta sigma-V divided by 1 plus E0. Once MV is known from an odometer test, it can be applied to a field layer of thickness H0 using the second equation. A few points about the MV method. First of all, note the linear scale for the vertical effective stress. MV depends strongly on stress level. Therefore, it's important to determine MV over a stress range relevant to the problem being considered. It's very easy to use and therefore popular among geotechnical engineers. And there are corrections mu to odometer-derived values of the settlement for various soil types which are published in Tomlinson's textbook.